Now in the next session, we will study an example how to solve the thermal analysis. In the previous video, we have already understood about what is thermal analysis and the basics about thermal analysis. We have also understood the different types of heat transfers. So in this example, we are going to consider a gearbox housing which is mounted on a gearbox. Now when this gearbox housing is mounted on a gearbox, it is subjected to some temperature loads. Okay. Now the temperature loads are mentioned over here. The outside region of the gearbox housing is subjected to a temperature load of 60 degrees Celsius, and the interior surfaces are subjected to a temperature of 90 degrees Celsius. Okay, and we also have some convections. So what is going to happen, this object over here that you see on your screen, it is going to be subjected to some temperature loads, and while that is happening, it is also giving away heat to the ambient temperature. So the convection on the outside area, on the outside surfaces of the gearbox housing, it is subjected to a convection of stagnant air. Now the outside atmosphere is air, so the coefficient, we will understand how to apply that, how to apply this condition in Ansys Workbench. The ambient temperature is 20 degrees Celsius. Okay, so this is what we have. We know the data now. The material that we are going to use for this gearbox housing is aluminum alloy. Okay, so now let us see how to perform this analysis. So we will come into Ansys Workbench. Once you come into Ansys Workbench, we will add one steady state thermal analysis. Now in this problem description, it is not mentioned that if the temperature acting on the body is for a specific time. So we will consider this to be a steady state analysis, right? So we will come to Workbench and I will add one steady state thermal analysis. We will change the name. The material that we are going to use for this analysis is aluminum alloy. So first let us add the aluminum alloy. Okay. Now please make sure that the material that you are adding should be from the thermal materials, because if you take it from the general materials, it might not have the thermal data into it. So it is very important that you take it from the thermal material. So make sure you click on the thermal material data source and then you can take the material. Okay, or else when you go to the general materials, when you add the aluminum alloy, you can check whether this material is having the thermal properties. So it is having the thermal properties. Okay, it is mentioned over here. Okay, now we will return back to the project. And now we will enter into the geometry. Now the geometry that we have to use in this example is a gearbox housing. We can create it in the CAD software. So we have already created this. And now we will import this. Once you import it, you can double click in the geometry. Set your unit systems and then generate the model. Once the model is generated, you can perform some optimization process. For example, I don't need these cutouts or these slots, so I can just remove them. So I'll come to tools option and we will use the fill tool to fill this. Okay, similarly, I will also fill the other side. Okay, then we will use the Boolean operation and we will unite all these geometries. Okay. After this, if you want to perform some changes over here, we can do it. Now in this, after you have made all the necessary changes, now let us perform the analysis. So for performing the analysis, we can enter into the mechanical window. If you see, the model is exactly symmetrical, so you can also cut the material in the center over here above the ZX plane, and you can take half of the model. Okay, so all these things can be done. Later on, we will come into the model cell. Now when you come to the model cell, first let us understand what tools are available. Okay, so the model is open now in the mechanical window. Now this is the window that is opening when we enter into the mechanical window of thermal analysis. Now you can see over here, almost the window looks same, but the only thing is when I click on the steady state thermal node over here, the contextual toolbar shows all the thermal loads that can be applied on the body. So we have temperature, convection, radiation. If you click on this button over here, heat, you can apply heat flow, you can apply a perfectly insulated body, heat flux, or internal heat generated. And there are some other conditions also which we can use for our analysis. Next, because it is a steady state thermal analysis, you will observe that the runtime or the analysis time is only 1 second. Okay, if you remember, we discussed the same thing in static structural. In static structural also we discussed that the runtime means the analysis time is only 1 second. Okay, so we have understood this. So the first thing after we come to the mechanical window, we will apply the material that we need for this model. So the material has been changed to aluminum alloy. After that, we will mesh the model. So I can first create the meshing or generate the meshing using the default mesh settings. You will observe that the meshing is quite coarse. Okay, if you are not satisfied with the results of meshing, you can use the relevance option, or you can use the advanced size function, proximity and curvature, and in that you can use the default settings. We will see what results we will get. This might take some time because there are a lot of curved areas and small areas in the geometry. Okay, so you can observe over here that the meshing has been done. It has been refined in the small regions. You can see over here, wherever we have small areas, curved areas, there the meshing has been refined. Okay, the number of elements that has been generated now is 3,48,000 something. You can also check the element quality. We will have all the tetrahedral elements over here. So you can see the quality is quite good. We have somewhere around 0.6. Most of the elements are very close to the perfect shape. Okay, so we can see the quality, check the quality, and after all these things, then we can proceed with our analysis process. Okay, so let us continue. After the meshing has been done, now let us apply the loads. After the meshing has been done, now let us apply the loads. So in this condition, we have a temperature of 60 degrees on the interior surfaces of the gearbox housing. So we will click on the steady state thermal node and we will apply a constant temperature. So take the temperature option, select the surfaces. Okay, so we are talking about this surface where you need to apply a temperature of 60 degrees. Okay, So we will select that and we will apply, and now we will enter the magnitude of the temperature. So we will say it is 60 degrees Celsius. In case the temperature is given into kelvins, you can come to the units option and you can change the unit of the temperature to kelvins, whether you want it in Celsius or into kelvins. Okay. Next, it is said that there is a temperature, constant temperature of 90 degrees, which 90 degrees Celsius is acting on the interior. Okay. So we will go to temperature again, and now I have to select the interior areas. So we are going to select these areas. Okay. So all these surfaces which are there internally, they are going to be subjected to a constant temperature of 90 degrees Celsius. So let us apply it, and we will say it is 90 degrees Celsius. Okay. Now once that is done, after that it is also said over here that the exterior surfaces are subjected to a convection of stagnant air. So now what does this statement mean? If you notice in the problem, they have not mentioned the film coefficient, they have only said what is the condition in the exterior. So in the exterior condition is that of a stagnant air. Now there is an advantage in Ansys Workbench. If you know the situation of the atmosphere, you can directly import the values. Now see what we are going to do. We will add the convection option. Okay. First we will have to select all the exterior surfaces. So we can use the control key and you can just drag your mouse, so you can select all the exterior faces over here. Okay, you can select them one by one, or you can just drag your mouse on them so that they get selected. Okay, see to it that you select all the faces. This surface. So because there are a lot of faces, it might take some time. Okay, make sure you've selected all the faces. Okay, now we can observe that we have selected all the faces on the exterior, and now we will say apply. We need to mention the film coefficient and the ambient temperature. Now we know that the ambient temperature is 20 degrees Celsius. So let us enter that ambient temperature of 20 degrees Celsius. But the film coefficient we are not sure. But the only thing that we are knowing is that the outside ambient atmosphere is of that of a stagnant air. So you can click on this arrow over here and you can say that we need to import the convection values. When you come over here, there is some inbuilt convection data that is available in Ansys Workbench. Now you can see over here, we have stagnant air options and stagnant water options. Stagnant air, horizontal cylinder, simplified case, vertical planes, and stagnant water, simplified case. Now what does this mean? Whenever you say that it is stagnant air, you can select out of the stagnant air option, or whenever it is a liquid, whenever the object is surrounded by some liquid, that time you can select the stagnant water, simplified case. Okay, and stagnant air, and then you have the orientation of the geometry. For example, the object that we are analyzing, okay, the object that we are analyzing is in a horizontal manner or it is in a vertical manner. Okay, so now in this case the gearbox housing is something like this. Okay, so I can consider this to be a horizontal case. Or if you are not sure about the orientation of your geometry, you can simply take it as a simplified case. Okay, so now here you can understand that the data is stored over here. You can select that and you can say OK. So once you say OK, you can see over here that the film coefficient has been taken in the form of a tabular data, and you can see the value over here in the tabular data. So at 21 degrees Celsius, the convection of this atmospheric air is going to be this much. Okay, so this is an advantage that we have in Ansys Workbench, where if you know the condition outside, what is the ambient atmosphere like, whether it is air or it is some kind of a liquid, we can directly import these values from the data. Okay, so now the boundary conditions have been applied. You can see very clearly there are three loading conditions: temperature 60 degrees Celsius, temperature 1, temperature 2 is 90 degrees Celsius, and we also have convection. Now we are going to solve the model. So for results, we need to find out the temperature distribution in the design. So I will select the solution node. Now if you see the contextual toolbar, you have thermal options. You can find out the temperature, total heat flux, or the error. You can also use the probe option to find out the reactions. Okay, so now let us see. I can select the solution option, thermal temperature. So this is going to show me the maximum temperature distribution and the minimum temperature distribution in the entire geometry. If you wish, you can also add temperature distribution for one particular region. For example, I am only interested in the temperature distribution in this area. Okay, I am only interested in these two areas. I can add that. So instead of all bodies geometry, I can select these two faces and apply. So now this probe over here, or this result, is going to give me temperature distribution only in these two areas. Okay, now let us solve this. So again, now this will take some time because of the number of elements that we have generated. The meshing is very, very fine. Okay, so now the analysis has been done. We can click on the temperature option over here and we can see the temperature. So it is showing you that the maximum temperature is 90, the same that we applied internally over here. Okay, and now if I can see over here only this region, how much is the temperature distribution in this region. Okay, so this is how you can find out what is the maximum temperature distribution in the model. You can also request for the total heat flux that is generated. So I can solve this and we can understand what is the total heat flux in the model. So when you click over here, you will understand what is the total heat flux. So the total heat flux that is generated over here is 117.28 watts per millimeter square. Okay. Now whenever you talk about heat flux, you can see the arrows over here. Can you see the arrows in the contextual toolbar? When you click on the arrows, it will give you a graphical representation of the area from where the heat is flowing. Okay, the arrow size is quite small. You can increase the arrow size. Okay, you can increase the arrow size so you can clearly see them. Okay, and then you can see the animation over here, which will show from where and how the heat is flowing inside the design. So you can see in the animation. Okay, this option is only available when you have the total heat flux option. Okay, so this is how you will perform a simple thermal analysis for your design.